Hi, welcome to part 2 of Mr. Collins's tutorial on the chemical mole. This is part of the Introduction to Chemistry series. I'd normally be giving these as lectures at the beginning of Year 11 chemistry, but I wanted to do something different this year. And moles is usually what I would give at the end. I would actually talk about part 3, which is to do with the types of chemical bonds beforehand. But because of your assignment, the types of chemical bonds are less important. They're important in term 2, but the mole is very important for this term. So I've decided to talk about the mole a little earlier. And the mole is the cornerstone, the centerpiece of chemical reactions. Here we can see a few different types of chemical reactions. We've got an addition reaction, a dissociation reaction, a displacement reaction, and then a double displacement reaction. I'll link down to a video with Bill Nye, cheeky Mr. Bill Nye, on chemical reactions in general. It's a bit of fun, but more at a junior science level. And let's recap chemical reactions. So a chemical reaction is a change in which at least one new substance is formed. That's contrasted to a physical change, like scrunching up a piece of paper, or breaking some glass, or changing state. You've still got whatever you started with. You haven't created anything new. Burning paper, or maybe melting or making glass from sand, that would be an example of a chemical reaction. They involve the breaking and making of chemical bonds. So here we can see that hydrogen, it has in its first shell 1 electron. It wants to become 2 like helium, and so it would love to join up with oxygen. It would love to share that electron. That's what we call a covalent bond, which we'll go over in part 3. So both oxygens want to gain 1 electron, so their outer shell is filled. Here you can see oxygen, its first shell is filled, but it's got 6 electrons. It would like to have 8 in that second shell and become like neon, which would be 8 plus 2 for the first shell, an overall of 10 electrons. So they bond up like this and they share the electrons. Hydrogen's happy, it's got 2. The other hydrogen's happy, it's got 2, and the oxygen is happy, it's got 8 in the outer shell. That's a full shell like neon, like the noble gas, and 2 in the second shell. I guess 2 in the second shell is like helium. So why do chemical reactions occur from an energy perspective? Well, chemical reactions occur for 2 reasons. The first one is to decrease in energy. We call that enthalpy. And more stable electron configurations, like that of the noble gases, have less energy. Things tend to move from a higher state of energy to a lower state of energy. That's why if I release this pen, it starts to drop to the ground. It's going from a high state of gravitational potential energy to a lower state. The other thing is, and this is something we won't focus too much on, but it's quite peculiar, is that things like to increase in randomness. Things don't like to be ordered, and order is actually quite rare to find. If you have an ordered packet of Pringles or something like that, you know how they come stacked and ordered, and you release that onto the ground, they're not going to become more ordered, and they're not even going to maintain their order. They're going to spontaneously become more disordered. And that state of disorder is what we call entropy. And chemical reactions actually occur not to get necessarily a lower energy, but actually to become more random. So maybe a gas at room temperature, things like to be random. Gases are quite random as opposed to a solid, which is a lot more ordered. So chemical reactions, let's talk about enthalpy. In terms of the energy side of things, they can be exothermic. That means they release energy. Exo means outside, thermic means thermal or heat, so they're releasing that heat. And so if you have an exothermic reaction and you touch the test tube, it'll be hot afterwards, or like an explosion. It's releasing energy as heat, light, and sound. Endothermic means to enter or within, and they absorb energy. You might have seen these from junior science where you get a chemical reaction going and then the test tube is cold. It's actually taken in heat from the outside surroundings and drawn that heat into itself. So those chemicals actually started from a lower state of energy and went to a higher state of energy, and they got that energy by drawing heat from outside of themselves, and that's why the test tube ends up being cold. That's a lot more uncommon though. Most reactions are exothermic. And of course we've got reactants, sometimes called reagents. That's what we start with. and products. That's what we finish with. You can see here an example of a chemical reaction, 2 molecules of H2. So that 2 refers to that there's 1 and 2, and that H2 says that each molecule is bonded together. And they're reacting with oxygen, O2, to form 2 H2O. That's a balanced reaction because we've got 2 oxygen atoms on the right-hand side, or the product side, and they're balanced by the 2 oxygens on the left-hand side, or the reactant side. The same goes with hydrogen. In this case, we have 4 and 4. I'll link to this video in the description as well. It talks about where atomic theory originally came from, and it's quite interesting. And I think it's always useful to look back in history to find out, where do these equations come from? Where do these ideas come from? And by understanding the history of chemistry, that actually helps you do chemistry in the now. Let's talk about chemical equations again. So chemists use equations to describe what is happening in chemical reactions. So for an example, a word equation could be phosphorus and chlorine gas create phosphorus trichloride. It takes a long time to write out. So chemists say P, the symbol for phosphorus, is added to chlorine gas, Cl2, and that creates phosphorus trichloride, PCl3. What you'll notice here though is we're starting with 1 phosphorus and we're ending up with, well, just 1 phosphorus. That's balanced, but we're starting with 2 and suddenly we're getting 3. That's unbalanced. It's as if when we do the reaction, we get the universe gives us another chlorine atom. That doesn't happen. There's this idea that a chemist called Antoine Lavoisier theorized, and that is the law of conservation of mass. That means that reactants always weigh the same as products. You're not going to lose any mass. A balanced equation demonstrates this, as both sides of the equation have equal number of atoms. So to balance this out, we're going to have to put a 2. Now we can't simply just change that to a 2. Otherwise we wouldn't have phosphorus trichloride, we'd have phosphorus dichloride. But we can create 2 separate molecules, and that's what we're doing when we put that 2 there. That's the coefficient. This had a coefficient of 1, which we didn't need to write in because it was just 1. It's just 1 phosphorus trichloride. Now 2. So I usually start when I'm balancing equations with the biggest atom and then work backwards from that, or a central atom. So 2PlCl3. Now, if we go from this original equation, we just put a 2 in there. That means that phosphorus is unbalanced. We have to put 2 phosphorus. And then with the chlorine, well, that's now 6, so 3 times 2, now we've got 6, so that's balanced there. Antoine Lavoisier, father of modern chemistry. As I said, it's important to have a look at the history. This video, it's not going to teach you any theory, but it is an interesting look at how he actually, how he came up with the law of conservation of mass. And he was actually looking at hydrogen and oxygen, and create water, and then you go back to hydrogen and oxygen again, then you go back to water. And he was the father of chemistry because he was the first to really make a big deal about being accurate. Because being accurate is what chemistry is all about. Do I have 14 grams or do I have 14.015 grams? And in your calculations later on, that'll actually make a huge difference. So he designed experiments where he needed more accuracy than the apparatus available to him at the time. So when he designed his experiments, he'd also design really accurate thermometers, really accurate mass scales. And he eventually got his head chopped off in the French Revolution. Poor guy. I wonder what he would have been able to achieve if that hadn't happened. Interesting fact, he also worked with his wife. And she was his lab tech and also co-partner. So one of the first women really making an impact in the chemical field. So chemical equations, remember you cannot change the molecules themselves. You can only change the coefficient in front. Now steps how you do it. List all the substances involved, that's the unbalanced equation. Then balance the equation by only changing the coefficients. You cannot change the subscripts, otherwise you'll change the molecules themselves. There's really no trick except for practice. Although some students do like to write out in brackets below the number of individual atoms they have, although that should become pretty obvious to you once you start understanding what a subscript means and what a coefficient means. So that would be another example of a balanced equation there. Here are some balanced equations for you to try, and I'm going to give you the answers. You might like to pause the video and try them, but I'm going to give you the answers in 5, 4, 3, 2, and 1. There's the answers though, there. Although that 1 doesn't need to be there. And that one, and that one. But that's just to show that they could be there, but in practice, there's no point. It's arbitrary, it's redundant. If you'd like to try some more chemical balancing, the balancing of chemical equations, you can search online. There's tons of interactives. A particularly good one is by Fett at Colorado University. Just type balancing equations, PHET, into Google, or copy out that long URL and you'll get what you need. Works on iPads as well, HTML5, which is great. So let's talk about the mole, the star-nosed mole. It's actually got one of the most impressive sense of smells. They can smell worms underground when they're meters and meters away. That's how they get their food. No, of course, that's not the mole we're talking about. We're talking about moles on people's faces. Now, moles can actually become cancerous, so you need to make sure you go to... No. You can check out this clip talking about moles from Austin Powers. I'll link that in the description. It's totally unrelated to chemistry, but it's just a bit of fun. Of course, we are talking about the chemical mole. But before I talk about the chemical mole, which actually is derived from the word molecule, a German word, molecule, that was a German chemist who first came up with the idea, we need to understand what a number actually is. Because let's say I have one apple and I've sliced that into 8 slices. Do I have one thing or do I have 8 things? Well, kind of both, because I have one apple, but I have 8 slices. So a number is useful only when it has units attached to it. So before I get into what a mole is, you need to understand what the significance of units in chemistry and maths in life are. And I really recommend this video to help you understand that. So take a moment, watch this video, and then come back to this video. Okay, so now you've watched this video, I want you to understand that a mole is a number that chemists use as a unit. So a dozen is 12, a couple is 2, a score, you might be familiar, is 20, and a mole is 60221. I'm not going to try and say that. So we use scientific notation to write the mole easily as 6.02 times 10 to the 23rd. So I've done that to 2 decimal places. You can go further than that, but usually 2 is okay. Some chemists like to use 6.022. And moles are given the symbol N, not M, but N. Why? Because M is already taken, meters, right? If you want to make it abbreviated a little bit more, MOL. Don't include the E on the end there. Maybe just like a dozen is shortened to does. Now, you can express any unit, boats, grains of sand, smiles, in moles, but chemists mostly use moles with the unit molecules. So, a mole of smiles, that would have to be more smiles than 1,000,000 years of human history. Because the mole is an incredible number. There's probably not. Actually, there probably is. Think of all the grains of sand on Earth. That might be close to a mole. In fact, I want you to appreciate how huge this number is. How huge this number is by watching this video. It's mind-bogglingly huge. It's bigger than what you can even... If you had a... Anyway, watch the video. I'm getting a bit too excited. And I'm assuming that you've gone to watch that video now, but if you're still struggling with this concept of a mole, I really recommend this video. I can't share the link, but it is on ClickView. And if you do download the PowerPoint that I've uploaded to Blackboard, then I'll put a link to it there. So but obviously I can't put this link on YouTube as it is a copyrighted video. So I really need you to understand this concept of a mole, and maybe you're starting to get it in your head, but it's a good idea that we do some practice. So let's forget about moles for a moment and let's create a new unit, a rap. And 8 is a rap, okay? Like 12 is a dozen, 8 is a rap. So if I have one rap of paper clips, how many paper clips do I have? Well, of course, I have 8 paper clips. If I have, now let's change it from paper clips to oranges. If I have 2.02 wraps of oranges, how many oranges do I have? Well, since one wrap is 8, so I'm going to have 2 times 8, which is 15, just jokes, 16. Making sure you're listening. How many DJs in 3.5 wraps of DJs? Well, you can keep going. Oh, sorry, I didn't give you any warning. You can keep going through those. I'm going to give the answers in 5, 4, 3, 2, and 1. All right. Let's change wraps to the number of the day, the mole. Now, the only difference between a rap and a mole, or a dozen and a mole, is just a mole is a massive number, and the scientific notation can be a little confusing. It doesn't have to be though. So how many paper clips in one mole of paper clips? Well, of course, we'd have 6.02 times 10 to the 23rd paper clips. How many oranges in 2.02 moles of oranges? Well, we'd have 2 times 6.02 times 10 to the 23rd. So that is 12.04 times 10 to the 23rd. Or it's 1.204 times 10 to the 24th, depending which way you like to write your scientific notation. Anyway, I'm going to let you try the rest of these and give the answers in 5, 4, 3, 2, and 1. How'd you go? Now, what you've actually been doing is using a formula. You've actually been using the particle formula. And it's simple maths. It's just how division works. So, number of particles, if I have, you particularly did it for this one here. If I have 40 gummy bears, that's the number of particles I have, and I want to know how many moles, I've got to divide it by the number of particles in 1 mole. So that's Avogadro's number. I encourage you, if you want to use the particle formula, it doesn't come up really in chemistry, but it does help you in maybe a chemistry exam, but it does help you understand, I guess, the maths behind what you're doing in chemistry. You can try the mole particle practice worksheet. This formula you were already using. I want you to understand that, I really want you to understand what you're doing instead of just, oh, I need to use this formula. Because if you're always working at which formula do I use? I forget what the formula is. You're not going to be able to succeed at those A levels. An A-level student actually understands the concepts well enough that they don't need a formula because the formulas are obvious. Well, I mean, of course, if you have, well, let's think about this. If I have, let's not talk about Avogadro's number in this formula. Let's talk about dozens. So if I have 24 loaves of bread, that's my number of particles. In this case, it's not particles, it's bread. And if I want to know how many dozen loaves I have, well, I'll divide that by 12. So obviously, if I have 24 loaves of bread, I've got 2 dozen loaves. So you do 24 divided by 12, and that's going to equal the number of loaves. It's the same with number of particles. Moving on. Why couldn't we have just chosen 6 times 10 to the 23rd? Why couldn't we have chosen something a little easier to remember? Why don't we just choose 15? Certainly easier than 6.02 times 10 to the 23rd, right? Well, I want to show you why 6.02 times 10 to the 23rd is the perfect number to measure things chemically. The best number. Better than grams, better than anything. This number is the perfect number. It's the only number. And I'm so glad that chemists were smart enough to use this number as the number for a mole. Let me show you why. Now, part 1, I talked about the mass of atomic particles, and we had a look at how a nucleon, which refers to the particles in the nucleus, protons and neutrons, they weigh roughly the same, and pretty much exactly that number there. So 1.6605 times 10 to the negative 24 grams. Now, of course, scientists don't want to have to write that out all the time when they're listing the grams that a particular atom weighs, the weight of a particular atom, or sorry, the mass of a particular atom. So they came up with the atomic mass unit. So one atomic mass unit is that number there. It's the weight of one proton or neutron. So lithium, it has an atomic mass of 6.9, roughly 7. So we can tell that there's 7 particles in the nucleus, because 3 of those here, 3 of those are obviously protons. That's why it's lithium. Otherwise, if it was 4, it wouldn't be lithium, it would be beryllium. But since it's 3 and the total is 7, that means it's got 3 protons and 4 neutrons. 3 plus 4 is 7. Good maths. Quick maths. But let's try this out. So if you divide 1 by 1 AMU. So 1 divided by the weight of one atomic mass unit. Put that into your calculator. 1 divided by 1.6605 times 10 to the negative 24. You'll find that the answer is exactly a mole. What? You'll find that the answer is exactly a mole. But what does this mean? Well, what this means is awesome, because it allows us to use the periodic table for 2 purposes. That mass number can now refer to 2 separate things. So the molar mass, this is the molar mass here, is of a substance, is the mass in grams of 1 mole of that substance. What do I mean? Well, if I have a mole of lithium, that's 6.02 times 10 to the 23rd particles of lithium, I know that that is going to weigh exactly 6.941 grams. And there's a symbol for molar mass. We use capital M for molar mass. But because 1 mole and 1 atomic mass unit are the inverse of each other, the mass number of, or a molar mass of an element can be used to express both the molar mass, what I was talking about just before, or the atomic mass, the weight of 1 atom in atomic mass units. So if I've got 1 atom of lithium, it is going to weigh exactly 6.941 atomic mass units. If I've got 1 mole, which is a lot more than 1 atom, it's actually 6.02 times 10 to the 23rd lots of atoms. If we've got 1 mole of atoms of lithium, it's going to weigh exactly 6.941 grams. Now remember, it probably would weigh 7, but remember there's some isotopes of lithium that actually have 3 neutrons instead of the normal 4. And even though they're very rare, when you average it out, the average is slightly less than 7. You can go back and look at video number 1 on isotopes if you would like more information about that. So it's an incredible thing. That number can be used both to describe a huge number, which we can measure in our hands, or just a tiny, a huge number, a mole of lithium, or just 1 atom of lithium. So this is an important skill for you to be able to find the molar mass of any substance in chemistry. And you use your periodic table to find that. You'll be doing this all the time. So carbon. I want to find the molar mass of carbon. Well, it's 12.01. That means if I have 1 mole of carbon, so 6.02 times 10 to the 23rd atoms of carbon, it's going to weigh exactly 12.01 grams. Silver, that weighs 107.87 grams. Now, let's say we've got N2, nitrogen. Well, 1 nitrogen is 14.01, so 2 nitrogens are going to be 2 times 14.01, so that's 28.02. You can do it for more, that should be a capital O, you can do it for more complicated molecules as well. Lead nitrate, sodium acetate. Why don't you try these? And I'm not going to give you the answers, but just typing in these molecules into Google, you'll be able to find on the Wikipedia page, for example, the molar mass of all of these molecules or formula units in the case of lead nitrate and copper 2 iodide. All right, it's time for a learning check. Let's take that theory and do some questions to make sure we've understood it. Let's stop talking about moles so that when we do start talking about moles, things might make a little more sense. So a mouse weighs 2 kilograms, and I have 4 kilograms of mice. How many mice do I have? Well, if one weighs 2 kilograms and I have 4, well, clearly I have 2 mice. What if I have half a kilo of mice? It's a big mouse, 2 kilograms, probably more of a rat. But anyway, if I have half a kilogram of mice, then, no, I don't have a full mouse. I've maybe got like its head or something like that, just a quarter of a mouse. You can do some more of these questions. You can pause the video and I'll give you the answers in 5, 4, 3, 2, and 1. What you've actually been using there is the mass formula. In this case, it was mice or monkeys. It wasn't moles, it was in mice or monkeys. But you effectively looked up the monkey mass or the mouse mass, or I'm trying to make the point that that's similar to our molar mass, and you divided that. You took that number and you divide it by the mass that you actually had. So in the case of the first example, you have 4 kilograms of mice. So that would be your mass there. But how much does one mouse weigh? Well, that is 2 kilograms. So you do 4 divided by 2, that gave you n. Well, it gave you the number of mice, which in this case was 2. It's the same thing. This is the mass formula. I never learnt the mass formula in school. It was just, I learnt about the mole, and then it became clear what I needed to do. So it's a bit, though today we teach you these formulas. Now, if you're going to work from a formula your entire life and not actually get the concept behind the formula, you're going to have a hard time. And that's what I aim to do today. That's why I'm doing this video, for you to understand the reasoning behind the formula. So you don't need the formula. I mean, the formula is given anyway in grams per mole are. Check this out. Grams per mole. Grams divided by mole. That's the formula. Grams divided by mole. So there's a few grams to mole calculations and a moles worksheet that I'll link to that will give you some more of these questions to do. Well, let's do something interesting.